Hi everybody. So up to this point we've talked about pretty much everything we need for all of the physical quantities that can describe rotational motion, but there's one still missing, and that's going to be the rotational analog of force. Now let's think about what we know about force. According to Newton's second law, if I apply a force, I'm going to get a change in momentum within a certain amount of time. If the mass is constant, then I can say that that's also going to cause an acceleration, and that's our classic sum of the forces equals ma. But how does that apply in rotational motion? So let's imagine that I've got a disc, a wheel, or something sitting here, and it's just sitting there, it's not rotating at all. So its angular velocity is zero, its angular acceleration is zero. If I want it to start moving, I've got to apply some kind of angular acceleration. I've got to get it to start spinning. And if you think about it, I'm changing its angular velocity, therefore I must have an angular acceleration. So a torque is what we call that analog of force. It's what's going to make it start moving. It's what's going to give it that angular acceleration so that it will start turning. Once we've got our angular acceleration, then we can use our rotational kinematics just as before. So that's what we're going to look at now. What is this torque and how do I apply it to a problem? Let's get started. All right, so we're going to start out just like we always do. We're going to take one of our already known equations for translational motion, for linear motion, and we're going to use our rotational analogs to convert that into an equation that will apply for rotational motion. So we're looking for an analog of the force. Well, the best equation that we know of for using the force is going to be Newton's second law. So go ahead and write down a mathematical expression for the relationship between the force and the acceleration. Well, you should already know how to do this, right? Newton's second law simply says that the sum of the forces, which is a vector, must equal the mass times the acceleration. Now, what were the conditions for that to be true? We have to have a constant mass. If I don't have a constant mass, well, then I'm simply going to have to do it in terms of the change in momentum with respect to time, the derivative of momentum with respect to time. Right. For starters, though, we want to find the relationship between the force and the acceleration because we're going to assume that I have a constant torque, which is going to be the analog of force, so that I can use it with rotational kinematics. All right. So now I want you to pause the video and I want you to write down a rotational analog for Newton's second law. Use our substitutions that we've done before and come up with an analog for it. Pause the video. Do that now. You got it? All right, well, the rotational analog of force we just said was called torque, and we use a Greek letter tau for that. And that is a vector. And it uses the same right-hand rule that we've talked about before. So it's going to be positive if it's going this way, it's going to be negative if it's going this way. And then now that's equal to the rotational analog of mass is the moment of inertia, and the rotational analog of the acceleration is the angular acceleration, which is also a vector. So the direction of the torque now is determining the direction of my angular acceleration. If the torque is positive, then my angular acceleration is also going to be positive. So that makes sense. All right, so that then is the equivalent of Newton's second law for a rotational motion. And remember, if I'm going to use my rotational kinematics, which we're going to give an example of here in just a minute, I need to know what that angular acceleration is. So the torque is telling you what that angular acceleration is. All right. So what is torque then? Well, we've kind of used this before, although we didn't talk about it. But take a look at the diagram here. I'm going to make it a little bit bigger so it's easier to see. So we had some distance r, and we started that turning this way with some force acting on it, right? So when I pull on just this edge, then that's going to cause this disc to rotate. So that basically is what a torque is. A torque is a force applied at some distance from the axis of rotation. Right? So just like we've always done, let's look at the two variables, in this case the distance from the axis of rotation and the force we apply, and let's come up with a definition for torque. Turn to the next page. All right, so here we have two situations in Microtest 1. Suppose we've got a large valve that controls the shutoff for an underground gas tank that's about to explode. We really want to get this turned off very quickly. So to turn it, what that means is that I need to give it some rotation. All right, so I'm going to turn it in a clockwise direction so that I can tighten that valve. All right, In one case, I'm going to apply a force over this short distance r, and for another case, I'm going to apply it over this long distance r. Now this distance r, this distance away from the center, away from my axis of rotation, this is called the lever arm. So it's not lever arm, it's actually lever arm. So the lever arm is the distance from the axis of rotation that I'm applying my force. All right, so for the same force, which will produce a larger torque? And remember, the torque is going to be what's going to make it spin. So we want it to spin faster so I can get that valve closed as quickly as possible. Which one's going to cause a larger torque? The short distance for the lever arm or the long distance? Think about it and make a choice. Well, you've probably seen, based on your own experience, if I've got this big wrench, I can turn things a lot easier than if I have just a short little wrench. So the longer the distance then, the more torque I'm going to be able to apply. Okay, just like we've always done, we change just one variable at a time. So now I'm going to have the same lever arm, but I'm going to apply different forces. Which one of these is going to make it rotate the fastest? A large force or a small force? Well, that one should be pretty obvious. The harder I push on it, the faster it's going to turn. So a large force is what's going to change it. So now that we've identified our two variables and our physical quantities that are coming into play, we need to decide, are they directly proportional or are they inversely proportional? So how about the torque in the lever arm? As the distance went up, the torque went up. So they must be directly proportional. And so we know in our mathematical expression then, we know that that is going to be in the numerator. All right, how about the relationship between torque and force? Well, a larger torque meant a larger force meant a larger torque. So they're also directly proportional. All right, so that gives us what we need to write down our equation, our definition for torque. All right, so we now know that our torque, it should be a Greek letter, which is a vector. Let me clean that up just a little bit here. Our torque, which is a vector, must depend upon the force, which is a vector, times that lever arm, which is also a vector. Now we know that when we multiply two vectors, we have to choose either the dot product or the cross product, the scalar product or the vector product. Up to this point, we've almost always wanted a scalar, like when we were talking about work, for example. But this time I want the result of that multiplication to be a vector because torque is a vector. So which one of these types of multiplication, types of vector multiplication do I want to use? Do I want to use the dot product or do I want to use the cross product? Well, the cross product is the vector product, so I need this. So this then is going to be my final result for the torque. All right. And if you don't remember what a cross product is, well, that just means that I'm applying it at this perpendicular. And so if the angle between the two of these is 90, then I can say it's F times R, the magnitudes. So if I have A cross B, that's the same thing as saying AB sine theta, where theta is the angle in between these two. We can also do this with matrices. You've probably seen this before. If I've got an I hat, a j hat, and a k hat, and then I can put down my components of my a and b vectors, and I can resolve that and figure out what the cross product is there as well. In our case, though, we are applying it at a right angle, and so a cross b is just equal to a times b, right, times the magnitude. Because they're at 90 degrees. Notice that they are no longer in the same direction. If they're in the same direction, I'm actually going to get 0. I'm not going to get anything at all. So let's apply that. So looking at microtest 3, suppose all the forces applied in the same direction as the lever arm. So here's my lever arm. Let's draw it here. And I'm going to apply my force in the same direction. So let's say that I'm applying my force this way. Will the robot rotate? No, right? You can think about that. I'm not pushing it away, so it's not going to rotate at all. However, will the robot translate? Absolutely. This is what's making it go straight forward. So applying this force in the same direction as my lever arm is not going to make the robot rotate. And so if you think about it, if this is the robot, and here's my axis of rotation. If I push it right here, my lever arm, let's do that in red, this is my lever arm right here. That distance is r. But because my force is in the same direction as that, there's not going to be any torque, but it will move. It will move in this forward direction with some velocity because it's now got a linear acceleration. All right, so suppose all the force is provided perpendicular to the lever arm. So let's see how that's different if we're looking at our robot here. So we've still got our lever arm, that's r, but now my force is going to be applied this way. So will that cause my robot to rotate? Yes, right? You see that it's now going to rotate this way. Will the robot translate though? No, I'm just going to, if I'm just sitting still and I apply a force here, I'm directly on the edge here, then I'm just going to rotate and I'm not going to translate at all. Right? So you see that I can have two different types of motion depending upon whether the force is applied off from at some perpendicular distance or whether it's applied in the same direction. All right, let's look at the next page. All right, so now we've got a really practical scenario. So I'm looking at my robot from the side, for example, right here. So there's my robot, there's his sensor. And I want to start this wheel turning. So that wheel is connected to a motor that's applying a torque to it. Once I get that torque moving, then I can get my wheel moving from this. All right, so suppose my robot motors are applying 0.49 Newton meters of torque. And the tire, the wheel here, has a radius of 0.20 meters and a mass of 0.50 kilograms. How long will it take the motor to get the tire rotating to an angular velocity of 30 radians per second? All right, so our scenario then is we're going to apply a torque to give an angular velocity. So get that wheel rotating with that. All right, well, here's our diagram here, but I'm going to blow it up just a little bit. So here's my wheel, and I'm going to apply that torque in this direction so to make it rotate. And then I'm going to, that looks a little sloppy there, shouldn't be connected. So I'm going to apply a torque to make it rotate. Get my pen back, there we go, in this direction. And I have a mass of the wheel, so we'll say the mass of the tire this time, the mass of the tire, and then I have a radius of the tire. All right, so step 2. So first thing that we're going to do is we're going to use Newton's second law for rotation, because we need that angular acceleration. Then we're going to use the angular acceleration that we get out of that and rotational kinematics. Because we know that we're going to have a constant torque, so I have a constant angular acceleration. So we're going to use rotational kinematics to get the time to our final omega. All right. Well, there's a few other steps we're going to need there. If we're going to use this Newton's second law, right, we're also going to need to find our moment of inertia. All right. So our quantities are this. So we've got our torque is equal to 0.49 Newton meters of torque, because it's a force times a distance. We know that our radius of our tire, which is also our lever arm here, that's going to be 0.020 meters. And then my mass of my tire is going to be 0.050 kilograms. All right, I don't know what I is. I'm going to have to find that, and actually that's what we're going to use our R for. So that's going to be kilogram meters per second. And then I know that my initial angular momentum or angular velocity is 0, and I want to know what is my final angular velocity in radians per second. Sorry, that's actually given to us. So that's going to be 30 radians per second, and what I'm actually looking for then is the time in seconds. All right, so now we've got what we need to get going. I am going to keep us on the same page here so that I can keep up with my numbers, but you should be able to go on to the next page. All right, so our step 4 then, we're going to need some equations. And so we already have decided we're going to use Newton's second law for rotation, so that's the sum of the torques is going to equal to I alpha, because it's alpha that we're needing. Now, which rotational kinematics equation will give me the time if I know the velocities and I know alpha? Well, that's going to be my velocity versus my rotational velocity versus time, my angular velocity. So I know that my final angular velocity, oops, not squared, my final angular velocity must be equal to my initial angular velocity plus alpha times t. So the only thing left then is to find I. Well, to find I, remember, we can look that up. We have a solid disk and it's rotating about the center. So you would go to your chart then and we would find that I is equal to 1/2 the mass of the tire times the radius of the tire squared. Okay. And that is going to give us what we need. All right, so let's go to step 5. So I only have one torque in the problem. So I know that my torque then, which is a vector, is equal to 1/2 mt RT squared times alpha. So it's alpha that I want. So let's go ahead and solve this for alpha. And so that's going to be the torque divided by 1/2 mt RT squared. And so that's 0.49 Newton meters divided by 1/2. The mass of my tire is 0.050 kilograms, running out of space here, and the radius of my tire is 0.020 meters squared. All right, so pick up your calculator. Let's see what we get. We get 0.49 divided by, we'll put all this in parentheses, 0.5 times 0.05 times 0.02 squared, and I get 49,000. So alpha then is equal to 49,000 radians per second squared. Okay, so pretty darn fast. All right, then we're going to go to our rotational kinematics equation, which is this. Now our initial is 0. I'm solving for t, so omega f divided by alpha must equal t. And so my omega f was 30 radians per second divided by 49,000 radians per second squared. And so let's do that, times 30, and I am getting a time of 0.000612 seconds. So let's putting that in something a little more reasonable. Then t is going to equal about 0.61 milliseconds, which is very fast. So that means that this robot will be able to get going to the speed that we want very, very quickly. So with lightweight tires, it's very easy for even a low torque motor to get our robot moving. And so that's why we generally don't put high torque motors into our robots. We just don't need them. So that's how we get the torque. And remember that that torque is giving us an angular acceleration. That's the key thing. Just like a force is going to give you a linear acceleration, the torque is going to give you an angular acceleration. Now, one comment. In engineering, we often refer to a torque as a moment. Anything that acts at some distance we refer to as a moment. That's actually where the term moment of inertia comes from. So in many engineering texts, you won't hear torque mentioned at all. They'll just simply say the moment is 0.49 Newton meters. Just know in your head they mean exactly the same thing. A moment is a torque, and a torque is a moment. We'll see you next time.